Hi. In section 10.2, we learned about the heat equation and learned how to solve at least one version of it. And that version looked like this. We had du dt equals some beta times d squared u dx squared for x between 0 and L and t positive. And we had sort of boundary conditions on the wire. So this was sort of the situation that we were working with, where we have a one-dimensional wire. And we assumed that the ends of the wire were kept at 0. And then we had some initial condition on the wire also. What was the heat of the wire at time 0? So that's 0. And that was f of x for x between 0 and L. Now, the fact that our initial that our boundary conditions were 0, that was super important because we used that to solve for our eigenfunctions. When we broke things down, we did separation of variables, and we had our x equation coupled with this boundary condition, and that 0 was really, really helpful. And then the other simplifying assumption was that there was no external heat source. So we sort of had our heat the way that it was, and then nothing changed to add heat from outside the system. But of course, both of these conditions are somewhat unrealistic because probably you're not going to be keeping the ends of your wire at 0 in any particular time. And then also you are usually going to have some sort of external heat source. So we want to we're going to look at a way to solve this problem with some slightly different assumptions. So these new assumptions are two things. One is that our boundary conditions are non-homogeneous. That is, u of 0t is some constant u1, and u of lt is another constant u2. Now, we're still keeping these constant, which is, again, maybe not super realistic, but we're upping the complexity of the problem somewhat. So these are probably not 0 in this case. And then the other assumption is that there is a heat source present that is independent of time. So again, we're still simplifying things. This is maybe not the most completely realistic situation, but we can only up our complexity so much at a time. So here's the new equation that we've got. du dt equals beta times d squared u dx squared plus our external heat source. Our new boundary conditions are non-zero, non-homogeneous boundary conditions. And our initial conditions are basically the same thing. We have u of x0 is some function of x. This is our initial boundary value problem. If we try to solve this the same way that we solved the last version of it with separation of variables, we will run into some complications because we have our non-homogeneous boundary conditions. So we're going to take a slightly different approach. We're going to assume that our solution u of xt is equal to some function which is independent of t plus something else, some w of x of t. And this makes sense because this is our steady state solution. And this is our transient solution. And by transient, we mean that W and its partial derivatives are going to go to 0 as t goes to infinity. So in your experience with how heat flows, as time goes on, if your external heat source isn't changing, you just sort of have this constant temperature, then everything in the environment is sort of going to go to a steady state that isn't going to change over time. And stuff that's happening earlier on in time is going to happen, whatever it's going to happen, but then it'll sort of, all of that transient stuff will sort of die off as time goes on, and you'll be set in a steady state that doesn't vary with respect to time. So now let's plug this in. Plug in u equals v of x plus w of x and t. And we'll get, so let's look back at our equation. So du dt is going to be the derivative of v with respect to t, but that's 0. So then we just get the derivative of w with respect to t. Then a beta times the derivative of u with respect to x twice. So we get a v double prime of x plus beta times the partial derivative with respect to x twice of w. And then we still have our p of x. And we'll squeeze in our x and t values here. It's an L. Now our boundary conditions, we'll just plug straight in. So we're plugging in x equals 0. So we have v of 0 plus w of 0 t equals u1, and v of L plus w of L t equals u2 for positive t. And then plugging in t equals 0, we get v of x plus w of x0 equals f of x for x between 0 and L. Now, what is going to happen as t goes to infinity? So let's take t to infinity. We get a steady state boundary problem. So w and its derivatives all go to 0 as t goes to infinity. So that goes to 0, that goes to 0. And then, of course, we don't really care about the initial condition because we're only thinking about what's going on when t goes to infinity. And so the problem that we end up with is we can move the beta over and we get v double prime of x equals -1 over beta times p of x for x between 0 and L. And then our boundary conditions, oops, I forgot to write that. This goes to 0 and this goes to 0. So our boundary conditions are v of 0 equals u1 and v of L equals u2. So this is a ordinary differential equation with just one variable, v double prime equals some function of x. And we can just sort of integrate this twice because we don't have a v in the right-hand side. So this is pretty simple. This solution we get by integrating twice. And I'm not going to go through all the details because I don't want to. but you can verify that this is the solution that you get when you sort of integrate and then plug in your boundary conditions. We get v of x is this really ugly thing, but again, it's it's ugly just because we're leaving so many things as letters. So integral from 0 to L of integral from 0 to z, 1 over beta p of s ds dz, and this is just because we had to integrate twice. So this whole bracket thing times x over L plus u1 minus another integral 0 to x, integral 0 to z, 1 over beta p of s ds dz. Okay, so this is ugly, but it sort of doesn't matter. We can get it. This is stuff that we can do because we know what p is, and we know what u1 and u2 are, and everything else is just sort of integrating variables. So now we have a v that satisfies this steady state problem. And if we think about this and go back to our blue problem up here, we know that v double prime equals negative 1 over beta times p. So if we plug that in here and here, those two terms will cancel. So since we know we can find a v that satisfies this, we use that over here, and our blue problem is going to become now our initial boundary problem reduces to time derivative on w dt equals beta times d squared w dx squared and so we're back to the problem that with the heat equation that we had way back at the beginning with no external heat source. And again, we can go and look at our problem up here. If our v satisfies our v of 0 and v of L equals u1 and u2, then if we plug those in up here, then the u1 and the u2 will equal 0, or will turn to 0 for this new boundary problem. So what we get is w of 0t equals w L of t equals 0. So wow, we're back to homogeneous boundary conditions. And then again, let's go back to look at our initial conditions. We know what v of x is, so we can just move that to the right-hand side, and we're left with w of x comma 0 equals f of x minus v of x. So we're back to the initial boundary value problem that we know how to solve, that we did back in section 10.2. And the only thing we've changed is changed this initial condition. So how did this work? Let's sort of think about what we did again. We assumed that there are basically two phases in this problem. One where the heat is changing a lot, and then that sort of dies off and we're left with a steady state. So what we did in green was thought about, well, what will that steady state solution have to look like? And then we thought back to the earlier part of t, when t is not close to infinity. And then we sort of thought about how that stuff will be changing. So that stuff is the w, and this initial boundary value problem is talking about what is happening, how w is changing. So we know how to solve this problem. We solve this way back. We can do it with our eigenfunctions. So we know that w of x and t is going to be some sum of our coefficients times our exponential piece, n pi over L squared times t, times our sine functions, n pi x over L. And the way that we get our Cn so the Cn are determined by figuring out how to represent this initial condition as a sine series. So by the Fourier sine series expansion. Of the initial condition, where f of x minus v of x, we need to write this as the sum from n equals 1 to infinity of Cn sine n pi x over L, because that's what you are left with if you plug in t equals 0 up there. So presumably, if you're given f and you're given everything else, you can figure out v, and then you can figure out f minus v, figure out c, and so then our solution is u of xt equals w, say v of x plus w of xt, where there's our w and there is our v. So the point of showing this example is to show how we started off with a very simple version of our heat equation and came up with a solution for it. And then as we add sort of layers of complexity to it, we can come up with different approaches to it, which take the physical realities of the situation into mind, and then build up our solutions based on what we did for our easier problems, and hopefully break things down into something that we already know how to solve. And this is something that you see very often when you're doing differential equations. There are a couple of other examples in this section about how to solve other versions of the heat equation that have more complexity. So one in particular is when you have two x dimensions, so two spatial dimensions. So like if you are heating a plate instead of a wire, and then you end up doing double Fourier series, and again, things get more complicated. I'm not going to go over that. I do recommend that you read these sections, and then if you're interested, reading the sections on the wave equation and Laplace's equation in the rest of the chapter might be interesting to you. I'm going to do one more video that talks about a little bit of the theory behind this, and then that will be the last of the material that I'm going to cover from the textbook.